Den hatte ich natürlich früher auch schon, aber mit Mail.
Ich dachte wegen an Shakespeare, an wen soll es gehen?
In German, if you want the translation, you can get headphones there and then translation. He is a member of the Chaos Computer Club.
Kannst du auf den Boden stellen.
Not only known for its efforts to turn
Also wenn du dich ausmachen willst du das überhaupt? Dann drückst du den großen Knopf. Okay. Aber sonst sind beide Mikros live? Ja. Die ganze Zeit? Ja. Okay.
Andreas Steinhauser.
So I don't actually know yet where this is heading, but I'm happy to take you on a small journey into the smallest and the largest of the things that we can actually even grasp cognitively. So these big topics, the large and the small, this is my topic tonight on at Fusion. So I was quite surprised that they actually said yes when I offered it. So my first question would be, what is science? What is scientific? And it's one of a very abused terms. So that's my first interest. We have 90 minutes, so if you can always ask questions in between, even random questions, because we have enough time to explain. So for the first one important difference for me is pseudoscience and science. Well, in terms of quantum mechanics especially, pseudoscience is very applicable. So there's a wide range of, nonsense basically. So there are a lot of people abusing basically these principles, even for fraud, for selling products like quantum healing, etc. So these are false promises made on a pseudoscientific basis where these people actually don't know anything much about the science behind it. So we have these products offered. This contains quantum science. This will be good for you. It's only €360. And I would like to use this talk also for you as a sort of service to be able to discern what's scientific and what isn't. So if just so that you can have the liberty to make your own decisions or make informed decisions. So that's only possible if you actually know these principles or these foundations. So I would like to start with an experiment. And first of all, you're the scientists and I'm the natural world. So I'm nature and you want to explore me, discover me, but I'm just the way I am because you're just, over there, just those blobs. Somehow part of me, but you're more or less intelligent and smart and resilient. And if you know this experiment already, please don't spoil it for the others. It's not my own idea. But so I'll be nature, and you can experiment on me to find out about nature. And I'll tell you 3 numbers. And you can continue this experiment, and you can then tell me 3 numbers in response. So my 3 numbers will follow a certain rule, and the 3 numbers that you tell me, I will let you know whether they comply to my rules. So basically, you only have to find out what are the rules. So my numbers are 2, 4, and 8. 2, 4, and 8. And now your turn for 3 numbers. Maybe someone from the audience. 8, 16.
So this is according to my rule. And if somebody understands the rule, and if somebody gives you the solution, I will tell if it's right or not. Times 2 is not my rule. The next 3 numbers, please. 1, 1, 1. This is not according to my rule. 1, 3, 7. This is according to my rule. Please keep on going. Please tell me more numbers. You can just tell me random numbers. 98, 90, 99, 98, 97. This is not according to my rule. This is wrong. 0, 0, 0 is wrong, but I'm sure you will find out what my rule is. You are intelligent scientists. My 3 numbers are 2, 4, and 8. Just to repeat, this is 2, 4, and 8. 6, 5, and 8 is according to my 5, 6, and 8. Sorry. Fibonacci is not my rule. That's not the correct answer. This would be a little bit difficult. This is a beginner's course. So random. 15, 16, 17 is here we found the rule. 3 numbers in a row. This would be the solution. But it's not about this rule. It's about how actually science works. And you've only learned something about my rule when I told you this is wrong according to my rule. And that's the difference between pseudoscience and real science. And pseudoscience just takes something for granted and then tells you that's the trailblazing theory. And this is the hottest science nobody has ever thought about, and it could be possible, right? So this is pseudoscience. But you cannot derive anything from that. If you take everything else into account, what you've excluded stuff, and you've just you've included zeros like 0, 0, 0. So you came closer and closer to the solution. And it was not, it wasn't Fibonacci, it wasn't other rules, but maybe backwards, this didn't work out. So you've excluded stuff, and this is how science works. Science does not work like to take a trip and think, I have this huge new theory afterwards. And it may be possible to find a solution like this, in this way. And there are certain scientists who work like this, but what you've got to do, you've got to sit down and you have to build a theory from that and then propose experiments. You have to propose experiments, not how to justify this, to verify these theories, but how to deny or decline theory. So this is the question of plausibility. Natural sciences is not doing anything more than that. The theoretical thing is done by the mathematicians, and please.
And so our hypotheses are controlled and or monitored by by experiment, and so we can make predictions. If these are my assumptions, then we're expecting a certain result from an empirical experiment. And so, if you're doing physics, then that means you're doing it right. If what we have is well, if we talk about quantum physics, mostly we're talking about quantum mechanics. I'll leave out the other parts. But one of the popular arguments is that, well, quantum mechanics, anything goes. It's just it's revolutionized classical mechanics. Everything's completely different, and we just don't know. And maybe this kind of thing could just happen again, that even today we might, it might turn out that the magicians were right all along, and then we just discover an entirely new kind of physics with entirely new principles. But that's not the case. The quantum mechanics didn't actually topple classical physics, but it complemented it. It made it better. And so this actually enabled physicists to make experiments for newly formulated questions that weren't which we couldn't find any experimental answers to before. And so I'd like to take you back to 1898. A young scientist, physicist, who studied physics, although his families and friends were against it or advised against it. But he had already, as a young man, said he wanted to study physics. People told him not to, due to the fact that, people just said, well, we've done everything, we know everything. So what was happening at the time was, electrical light, obviously, in the 1880s. Anything that was, sort of state-of-the-art, that needed some kind of, little glowing lamp. That was the hip thing of the time, what smartphones are today. And so this was the sort of scientific paradigm of the day, and of course there was lots of research going into this. So one question was, how do you make durable lamps, durable light bulbs? Because what you see is that a light bulb is obviously something like a heating system in itself. So it not just emits light, but also lots of heat energy. And so we have this young physicist who decided to improve the light bulbs of the day, and he was examining the light spectrum of the bulbs when glowing, because they emit different kinds of light. And for this kind of examination, you obviously have to make sure that the surroundings don't reflect. There's no ambient lighting, there's no other light source. So you have to find what is ideally a body that doesn't reflect any light at all, a so-called black body, or as black as possible. So that wasn't available as such, which was why he started to build a sort of enclosing box, and he made a tiny little hole into this box. So clearly, if it's the only way in. If the light is going to be reflected out of this sort of black box, it'll have to go in through the hole and fall in right the other end, sort of in reverse when it's reflected. But that's not exactly probable that what we can expect if a ray of light goes in a right angle, that it'll return at the same angle. So if we look into the hole, we can expect it's going to be glowing. It's going to be like light shining out of the black box at us. And the physics that concerns itself with glowing bodies, with heat and thermal systems of bodies, the warmer it gets, the shorter the wavelength of light that this body will be emitting is expected to be. This is the prediction of classical mechanics. But if I heat up the body even more and it's glowing blue, and if I heat it up even more, we would expect, well, what would it be then? It sort of even more blue, and then after that would be the ultraviolet spectrum, which isn't in the visible light spectrum anymore. So basically we would expect the light to vanish at some point, or just to go out. Something absurd would have to happen, but it doesn't. So this is the experiment. Just make this box sort of glow and just press even more energy in and observe that this weird effect that you expect doesn't take place. And so this is what was then called the ultraviolet catastrophe, not because the experiment was that dramatic, but because it really, surprised them as to the results. And the name of this young man, in fact, was Max Planck. So what did he do about this conundrum, this catastrophe? He said, well, obviously the formula, the mathematics has to be incorrect, and started doing lots of maths and found, basically a kind of mathematical shortcut to introduce a factor into this equation, which he called the Planck quantum. So, and that's what you often do with a constant or with an additional factor in an equation. And this is the h, or the h with a line, which you know from physics. This was what he introduced himself, as physicists do when the mathematics don't fit. And lo and behold, it was really the fact that with the addition of this factor, with the h, his formula actually was better suited to and so he said this is a sort of kind of corrective factor which improves the overall effect and the accuracy of the mathematics. And this he was hoping to kind of factor this newly introduced factor out again, and because it did have irritating effects, but he wasn't actually aware how brilliant this idea was, because it was a disturbance to the physics of the day. So he was trying to work around, even although he had already made the decisive idea at that moment. And so it was Albert Einstein who years later would actually recognize how brilliant this idea was, that it's a sort of successive addition of factors, but that wasn't actually clear to Max Planck himself.
So this means, according to Einstein, that energy gets transmitted. It's a packet-based communication in 1, 2, 3, or 4 packages, but it's not a continuous stream or any random number. But it cannot be divided into half or quarters or something like that. This doesn't work. It's not like it works. And he found it really funny and strange at the same time. So that what has been found out only recently, that light is a wave, is not right. So it's not the complete answer. Because there was an experiment, people were getting really frustrated, that should prove that light has a wavelength structure, the so-called anti-fusion experiment. And then you could see how the light gets diverged and then gets going across the whole scene. But I will see how this light spreads out all over the screen, and it gets from light to dark, and this is proof that light does not work only as a wavelength spectrum type across the screen, but you can prove this really easy. You can do this experiment on your own if you just make a wave in your bathtub, and then you will see how these waves diverge from the inner point from the bathtub. And this was a proof, or let's say a plausibility. And now Max Planck comes into it, and Albert Einstein wants to understand why and how. And it says, oh, this is bollocks. And light is not a wave; it's a particle. There are light particles for this certain wavelengths, and so it's not a wave. So this is the first big dilemma in physics. This is one of the big. This is a dilemma until today. So I can tell you already that light is both. It's a wavelength and the particle both at the same time, because I can do both experiments and it will verify this thesis. Albert Einstein didn't want to believe because he was a physicist. Not believe, but he experimented with this, and this experiment has become famous under the name of the photoelectric effect, and he could explain this like that. I shoot light onto a metal plate, let's say red light. Red light has a longer wavelength than blue light, and now I can build an apparatus with a ring, and I will just shoot this light through this ring, and if this light has enough energy, and it would hit electrodes. Electricity was just a new stuff. This was a hot shit on the block back then. And we are still in a time that was some crazy stuff, didn't really explored, and it wasn't really recognized physics. He was around 20 maybe back then, like you maybe. So now he experimented with this photoelectric effect, and he tried to build a theory around this. As a young patent office worker, so this is the only way he could finance this experiments. This was all done on his own. It was more situated in private life back then, not done in a university or something, but he didn't do this on his own. Mileva Marek, his then girlfriend, was the first Hungarian mathematician who also worked with him, and she gets never recognized. This is what really pisses me off. He wasn't a good mathematician, but his later wife was a really good mathematician, and she did part of this work, but it wasn't recognized. And to this day, it's still not fully recognized what was the part of Milena Marek in this, also in Einstein's work. And I can understand he was in a relationship. And if somebody has knowledge about certain topic, of course, we will change ideas, and ideas you will have never on your own. And this is why I would wish Mileva and Einstein, or Mileva and Albert, thought of that, because this would make it more plausible. Now they found out that if we shoot red light onto this metal plate, and then they could prove that there are no electrodes would come out of this ring, this electric ring. So you could prove that they didn't shoot out electrodes out of this metal plate. However bright this light was, and if this would be a lot of energy, it would hit how much energy you would ever use, if you would hit it really hard, one of the electrodes should come out, would get shot out, and then you could, of course, see this. But it didn't work like this. And if I shorten the wavelengths roundabout and direction to blue, yellow blue, from certain wavelengths, a lot of electrodes shot out of this massive plate. And no matter how powerful the light was, if you hit it with a really dark light, a lot of electrons would come out. This is actually the way solar energy works. This is photoelectric effect put into effect. So if I hit this metal plate at a certain wavelength, and if I would enhance, or if I would, the wavelengths would be higher, then this would
so individual little steps in physics is actually what we call quantified, or in discrete points, and that's, so we're in the middle of the topic now. So if I target this, if I throw light onto this metal plate, the effects will appear in steps, in discrete steps. And now it's going to get really weird. At the time, this was really a hot topic for young physicists. The old guys obviously didn't want to have anything to do with it. This was kind of a blasphemy. But the young crowd, Niels Bohr from the atomic model, Werner Heisenberg, also very young, 20 years old. So in that sense, Einstein is almost a classical physicist in age-wise, at least. Well, one more remark to the photoelectric electrical effect. It was Einstein who, it was for this work that Einstein received his Nobel Prize, not for the relativity theory, not for the equation E/mc squared, but for the photoelectric effect, or for his theoretical explanation, with 20 years delay nonetheless. But that can maybe show you how relevant it was. But back to Niels Bohr and Heisenberg, the young guys now getting on top of quantum physics, and they started experimenting, observing others, physicists' experiments, analyzing them. And of course, the famous double slit experiment. Anyone who's ever heard anything about the topic might have heard of it. This is actually the experimental proof that light is not a wave, or not solely a wave. The interference pattern that I see on the screen behind the double slit actually shows in its pattern itself that light cannot be only a wave, because otherwise it wouldn't be able to produce these effects. So, but on the other hand, as Einstein postulated, if light is a particle, then we would have to be able to determine through which of these two slits did this particle pass through. So we make a kind of polarization filter, say with a certain vertical polarization, you'll go through the left slit, and vice versa. You can make a very simple setup, and if you sort the particles in this way, you won't see, or rather the effect will collapse, or well, just be. The whole effect is basically non-existent as soon as I see these two lines at the end of the screen, which is basically a paradox, or that caused a lot of physicists to really lose faith, because that just couldn't be. So just by the observation this will make the light particles behave in this certain more orderly fashion. This is entirely impossible. This can't be the case that they'll behave differently just because they're being watched. And so the physicists started doing all kinds of, widening or adapting this double slit experiment, and until today we haven't really managed to clear up this problem. Light can't be fooled in that sense. They tried all kinds of tricks to observe it without being noticed and that sort of things, but it just doesn't work. You can't see where the light has passed through without destroying the wave function, or that's the collapse, without destroying the wave characteristics of the light. And now we're in the middle of the theoretical principle that applies here. So if we had the possibility to see both at the same time, we would be able to see where it passed through and where it arrived, basically. But that is, as Heisenberg showed in his relation, in his important work describing these effects, the wave and the particle characteristics. This is basically what Heisenberg's theory makes impossible. You can't find out about both qualities at the same time. That's the essence of Heisenberg's theorem. And today we still can't measure two at the same time, obviously, but today at least we know that we cannot ever know these two things at the same time. It's impossible to know simultaneously how fast a particle is moving, which direction, or where its position is. Either I observe the one and the other becomes very sort of obscure, or the other way around, and then so it's not a precise observation is no longer possible in that sense. This not deterministic, not quite clear and logical aspect is actually at the heart of all matter and at the universe, and But quantum mechanics doesn't allow this for the simple reason that if we had the possibility to know these two things at the same time, basically everything would be deterministic. There would be no coincidence, there would be no chance, there would be no free will. And so basically I do have to say it in this brutal consequentiality. Without Heisenberg, without this concept, we would have a deterministic universe. But luckily, that's actually not the case. Thank you, Werner.
So now we've got this correlation by Werner Heisenberg. Now you can do experiments that are even more crazy. I will spare the details. That can be done in a photonic crystal. This is not esoteric bullshit. No. Also, esoterics web pages use this, and they sell. Of course, don't sell the real deal. This is really sensational. They have no clue at all. In a photonic crystal, photons get split in a way so two come out that have half the energy, but are completely identical otherwise. They have completely identical assets. They have not only the same properties, but they are identical. This is really hard to describe. You can do experiments that work like so. I will just shoot a laser into a photonic crystal. So to the left you have one of the half of the photons, to the right you have the other half photons, and these are entangled. And these will hit semi-proof mirrors that let through half of the photons. And bizarre is, and not not to be grasped by a physicist or by a esoterian, is to tell you why. Because physics doesn't tell you why. This is the question of the philosophers or the theology. But the physics, they just answer the question how, not why. They just tell you 50% of photons go through, and the physics doesn't ask why. He does, and he's trying to find a mechanism that how this actually works. And the answer is not found until today. And the physics has come so far that he's telling you there is no mechanism. There is no mechanism that will tell you why this goes through or not. And this is that's actually what Albert Einstein thought that would be possible. So the photon gets this physical property, so to speak, by birth. For example, if a photon comes out of a light bulb, and there are going to be photons that go through, and there are those that don't go through. And maybe you've heard of Schrödinger's equilibrium equation. And you can do experiments, and you can prove, which means you can show with a certain probability, with a high probability, that there are certain aspects that are inherited by the light. And Mr. Bell has also talked about this. We will not go deeper into the Bell's equation, and this is just random if a photon goes through this special crystal or not. There is something like random procedure, random that has no to the others, and it's not random like a cube, or if I throw a coin, of course. But if I know all the aspects, I can still tell you how the coin will land. For example, there are now robots who can play better badminton if you know just the certain rules. With the same ratio behind this, I can tell you that there is no reason that it's really random, and I can produce two of these protons, and one of these goes left, one of these goes right, and they go through these semi-working mirrors. And to the right side, you have a 50% chance of the light going through. So let's say it goes through. And then it will work on the other side. It will go through two. These are entangled photons. And this is what Einstein already said, who didn't see this effect in his lifetime. But Schrödinger's equation, I think it's one of the most elegant equations in the whole universe that can actually tell you that entangled particles have the same behavior, even though they operate in different spaces. And if I take a look at this, and at the moment where it goes through, on the other side, it will do the same at the same time. Now you could say they have talked to each other because they didn't have this information or they didn't have this property in the beginning. Like I went through, you can go through as well. And this is what you can show. This is what you can show nowadays because but this had to be done by speed faster than light. But since Einstein, we know this is not possible. And this is really crazy stuff that we can see an effect that has effect on both sides of both particles that gives them the same properties, even though they're completely separated. You can just put one of the mirrors much farther away. You have the particle on the one side, it hits it really early, and on the other side you have another mirror that is much further away, and this hits much later, and we would just watch the particle that's going in further away. It went through. Now I can see because the other one should have arrived earlier. This was much earlier, this particle. How can it take effect on the other side? Because I've already noticed that the other side it went through, and so in after effect it would have went through too. So these two particles were one particle, and they go in the same direction. They go in the same way, and only at the point where I look at these particles, I will have this. And now it gets really philosophical. So the philosopher would interpret this as, does it need a conscience or not?
Consciousness. So this is not really an esoterical question. Do you actually need consciousness to make these decisions? This is not kind of hocus pocus, maybe. You can prove experimentally that this is the case. The light quantum doesn't pass through, and I'll see what happened. But as long as I don't look, it basically passed through the mirror and didn't pass through at the same time. It's basically undecided. This is a kind of complex state, and it stays in this messy, complex state indecisively until I make my measurement. And so basically the particle will only have made its decision at the moment in which I actually look into the box. This is like the first aspect of the wave particle paradox. And there's another one, though. This isn't only behavior limited to light particles, to photons. This can be seen in other parts of the atomic model as well. So our eye, just watching something. Use your eye to look at something, and that's actually already doing a measurement. There's another kind of experiment. I think it was Heisenberg, I'm not sure exactly. And someone said, sort of had this quip, well, wouldn't we all have to be watching the moon? What's if the moon, if no one sees it in the night sky, wouldn't it just disappear? Wouldn't we have to just be all observing the whole cosmos at the same time to make sure it doesn't kind of fall apart? But the question is, what's the situation in which we're making these measurements? Maybe is it the measuring instruments themselves, our eyes or mechanical objects, are part of this messy state of indecision. And that's still the case today. You can't say beforehand if a measurement is necessary, if an eye or an observer is necessary to make this world possible at all. And that's actually quite interesting fact if you think about it. If we accept this kind of premise, and physics basically forces us to, we'll just have to basically say goodbye to the whole idea that this world is something real and palpable. And I'm not even joking. So either it means our world isn't localized, it doesn't have a place, or it means they don't even exist. They're just a figment of our imagination, because if you, use your eye as a kind of proof, the photon would be, entering our eye, hitting the visual nerves, and this is even a physical, in quantum mechanics, this is even a kind of electron tunnel. This is all happening inside your head. So then we have an electrical impulse to the nerve synapses, purely quantum mechanical properties and effects. And so we have all these intermingled states in the brain, which when this information is passed on. So we can rightly ask the question at the end of the day, what has this photon decided, or did we make this decision for it? And it sounds very kind of cheesily philosophical, but it's actually a very practical question. Who makes the decision at what point in time if this photon actually went through the screen or not? And there have been several experiments submitted to this problem, but as I just told you, you can't actually do it in practical experiments. That's why we do a mental experiment, and it's very famous. Maybe you've heard of it. It's called Schrödinger's cat. So let's say I make a detector for a very simple single atom of an element like, say, uranium. And this is a radioactive. That means it's a random process of, and we can't exactly say whether this particle will be destroyed or will deteriorate in at a certain point. And so either a particle will be emitted from the uranium or not. So the cat will die only in case the uranium particle is emitted and the sort of poison is. And the idea is to like basically put the cat in the box. Again, I'm not joking. This the experiments do make it very, very likely that until I open the box, basically I won't be able to find out whether this poison has been emitted, whether the cat survived it's this episode in the box until the moment I open the lid. So in terms of physics, it's really the case that the cat is dead and alive at the same time until the moment I actually open the box. So here we have the situation. Heisenberg told Einstein about all these ideas, and the thing was that Einstein was very reluctant to, or just basically said, leave me alone with this kind of thing. But Heisenberg actually did what had to be done. He presented a theory which actually supported experimental observations and was consistent in itself. And so Einstein obviously wasn't very content with all this, because there's just this basic understanding that the world in itself is kind of consistent and more or less logical, maybe not in my dreams, but every morning when I wake up, physics, all the laws of the universe will be back in place and everything is more or less organized. But if we look at these seemingly objective laws, and start examining the rules themselves more exactly, we can actually see that these rules are not so strict as we think. They're all defined in terms of probability, just a kind of smear of events. There's a certain likelihood that if I look in this direction, this glass over here, if I just look and maybe look back, it could be possible that this glass disappears. Maybe it has an entangled electron on Alpha Centauri somewhere in outer space. this particular electron here in front of me doesn't have a place. It just has a certain probability that I'm going to find it in the same place once I look back again. And that was the effect I'd actually mentioned before, or I promised before, which we call quantum tunneling. And this isn't, well, this is also experimentally well documented.
So it will stay inside the box. This is what you would think, but Schrödinger's equation tells you that there is a probability that is not zero that you will find it outside the box. So all you need is enough electrodes, putting them into boxes, and at a certain point I will find an electrode outside the box, not inside the box. According to classical physics, this does not work, because if I have something that does not have sufficient energy to get out of the box, it will not go out. Schrödinger's equations tells you actually the opposite. It can work. So it tunnels through. Why? Because there is a probability that it will show up at the other side. Inside of the isolator, there will be a cable with high voltage, and then there's an isolator in the middle, but I will still find electrons on the other side. They have been beamed to the other side. And this word beaming, or to beam, is actually used in quantum physics. This is quantum transportation, and the higher the voltage, the higher the probability will be that it shows up on the other side. The probability that I will find this electrode inside the isolator, because it cannot be there because it's inside the isolator. So it comes from one side of the isolator, and then it gets beamed to the other side of the isolator at the same time, without ever being in between for the complete time. It has not been in the isolator. The probability is zero. So this electron has somewhat hopped to the other side without being in between. This is the nature of quantum mechanics. How much time is actually left? Because we also want to talk about cosmology. Do we still got some time? Oh, we're running out of time. We have to speed up. Because I want to talk about a certain point, an interesting point. Because it cannot be that an electrode is not a thing, and a proton is not a thing as well. So it's a thing like what you think that is actually tangible, material things. But atoms are made out of these elements. Anything you see is made of electrons, neutrons, but we have to be sure these things are made of quarks. But quarks are not actual things. That are not tangible things. That has no size. A quark, the quark is probably the best answer we have, that a quark has no size. I'm sorry, I didn't make that up, or I didn't think of that. I didn't bring this up, but with a high probability, a quark has no real size. A neutron or proton consists of 3 quarks, but you cannot tell this directly. You can only give a circa. It's only approximately 3 quarks. In truth, 90% of the mass of a proton and the energy, because E is mc squared, 90% of the energy of such a proton consists of spontaneous virtual things, virtual particles. Quarks and antiquarks. The nice thing about a quark and an antiquark, because if a quark and an antiquark meet, they are nothing. It divides into a quark and into an antiquark. You're laughing, but this is state of the art right now. This is what this proof. This is state of the art in physics right now. There are 9 times more quarks and antiquarks and so if I look at this, there are 3 quarks for sure, but the rest might be something we call quantic foam. The other particles can come out of this somewhat naturally, but this is really a short time, 10 by 34, 10 times squared, 34. Why, you can ask me after the talk, because everything that is shorter than this, everything. So this is not coming back to one rule of energy maintenance that speaks against this. So the particles you are made of, these particles are made of, that are mainly, or let's say around about 90%, that are spontaneously virtual parts, are made of virtually in spontaneous parts, and only in the middle, in the statistical middle, you can say, for example, let's say I weigh 100 kilos. This is not true, but let's say I weigh 100 kilos. So 90 kilos of my mass are spontaneous, virtual, created particles that will just show up during this Planck Zeit. So let me sum up. These quarks have no size, they only have one energy. So they also have a color. It's something different from color, what you would think of color. They also have power, but they don't have a size. So this is also bringing us to cosmology. And I think you've never heard something like a black hole, or you've heard also of the Big Bang, and everything that's existed could have been in this really small class, or a whole sun, or a sun may become a black hole that is inexplicably small. Of course, this is complete bullshit, but this is not bollocks anymore if you understand that the sun is the whole foundation of the sun actually is not made of real material, but all of these quarks who take up no size. So we see galaxies, we can see them. Little anecdote on the side. Albert Einstein and all the other ones thought the universe was made of only one galaxy because you couldn't see more. And the other stuff that would show up were just little wobbles in the sky. These were just some fuzzy things, and nobody could make out that these are real own galaxies. They were called nebulas because the technique wasn't advanced enough to see them. But then Edward Hubble came out with this huge telescope, and he was giving some hope. I can only tell. I can only follow certain lawyers.
So he was the one who discovered that there are actually loads and loads of galaxies, and just in the observable universe there are 450 billion galaxies, and an average galaxy will contain 100 billion stars. That's just grotesquely enormous. That's just really, really, really huge numbers, and that's why you have to ask yourself, how did anyone come up with the idea that there was something like a Big Bang at all? So Hubble was the first to observe, or the one to start these experiments at least. So further away a galaxy is, the faster they will seem to fly away from us, and that's basically the proof of the expansion of the universe. But, just following that premise, obviously, if it's growing, it must have been smaller at some time. And if you observe the things that are moving away with a greater speed, i.e. they're further away, then you can kind of reduce it back in time, or basically deduct how old the universe is just from this expansion movement. So if this is a distance from 8 million light years, we the movement itself, the sort of flight effect, it's well observable. You know it as a Doppler effect, but astronomers call it redshift. This is a relativistic effect, basically, which applies to light in the same way. So if the further away a galaxy is, they're moving away from us faster, and that means they tend towards the red spectrum of the light, because it has a faster speed. Like with an ambulance, that's the famous Doppler effect that sounds as if it's the tone is dropping. So light, obviously, from my standpoint, light will always go in all directions. But I don't see all of that light. But I see basically if you're looking at the screen over there, you can just use the emitted light to calculate the distance. But how do I know how bright this far, far, far removed galaxy is? Well, for that you need to know something else. There's a phenomenon in the life cycle of a star, which is called a supernova. This is a class 1 supernova if the star was of a certain type before. But this supernova is an enormous, bright, explosion, which for a certain time, just for about a month or so, this is a star that will glow for 1 month like 10 billion stars. That means it has basically the light effect of an entire galaxy. So if there's a supernova appearing, I can use this as an observation and look at the color and use that to calculate how far away is it from me, and how far, at what speed is it moving away from us. And so these supernovas in history have been used to calculate basically these Big Bang ideas. Which leads us today to the result, possible result, that we have an age of the entire universe. This is sort of state-of-the-art physics. Well, there have been numerous experiments in quite recent times, like a research station near the North pole, if I got that right, that's examining cosmic radiation. But if you think about this light that you're seeing from maybe a supernova or other observations, this is already 8 billion years old, the light that's coming to us. And out of all these calculations, well, today you can say that the entire universe has an age from Big Bang till today of about 13.7 billion years. So if we actually find something that's that far away, you hardly see that. Well, basically, we can't actually find any objects that are that old. 8 billion, maybe, but at that time, at the very, very beginning of the universe, it was so hot. Well, that was at a time when everything was hydrogen and helium, and anyway, so everything was an enormous ball of fire and heat. So before that point, there's a kind of 100,000 years of where you can't actually see anything older than these. Well, so 13.7 billion minus a few 100,000. That's the point at where we can start observing, and what we can see is the famous cosmic background radiation. And so, if something, well, from hundreds and thousands of years of age is going through space, the light arrives. If we find structures that are older than that maybe arose in the first 100,000 years of the universe, they wouldn't ever have. Well. Sorry, basically just these time scales just allow me to determine that space is basically a flat plane. That's quite surprising. It's not because Einstein talks about the distortion of space. It's not bent in that sense. I don't look around the back of your head, but I just look until the point where I can, looking into the audience until I can't see what's behind it anymore. And that's maybe the same looking back in time. And what we think today is that the whole universe, this whole Big Bang event came to place through a weird quantum fluctuation, that all these particles didn't find each other in the entangled particles didn't find their mate in time to get back together again and annihilate themselves accordingly. So we have a different situation. In all these equations, this would only be possible out of one singular reason, and that would be dark matter. Energy is basically the same as matter, but even dark matter, dark energy, and all the matter and energy that I actually see in the visible universe. If I add that all together, we have positive energies, we have negative energies. So we add it all up, everything that we have, matter and energy, and we have a total sum of 0. Believe it or not.
So summing up, if we take the relativity theory and quantum mechanics and cosmology, if we put these things together and ask the question of probability and plausibility, that the plausibility is 0. If I sum this up, the universe exists of nothing. So this, in the beginning, so this works out in the beginning, in a physical sense, that something is Sorry, if I could translate this, I will also get a Nobel Peace Prize. I don't know. Thanks.
So, not only cosmologists, it was the quantum physicists as well who tried with all that they could to find a counterexample to this. But the sad case, it's the truth. The universe is, in total, just nothing, zero. And if you think of dark energy and dark matter, dark matter is called dark matter because it's, basically dark and invisible, and that's something that really gets on physicists' nerves. They want to observe and want to find out things about the universe. And dark matter is actually at the heart of many of these effects. For instance, it's supposedly the cause that the universe is actually not only expanding, but accelerating its expansion, which means that these whole procedures are actually going quicker and quicker. So in a couple of billion years, we have basically a thinned out universe. Everything will just be torn apart from each other. So the rest of maybe our neighboring galaxies will already have drifted so far off that we're basically going to go into a just dissipated situation. A universe just trickles out at the edges. So not the idea that was sometimes put forward that after the expansion, the universe will just kind of collapse back to nothing. So it won't implode again. It will just sort of peter out at the edges. That's about 200 million years from now. But, I know these are quite sort of shocking announcements, but that's what nature is. Nature isn't there for us to, find it nice and friendly and according to our expectations. And all this is actually current state-of-the-art accepted physics. It's not esoteric, weird stuff. That doesn't mean that we're going to revolutionize all of physics again. That doesn't mean that it's not on clear terms, that we don't actually... Basically, we're just trying to add on to these ideas, but there's nothing to be done about the nothingness of the universe, and so I can just say, enjoy your time in the nothingness. And if you have any questions, please go ahead. I think there will be a microphone on the floor somewhere. Yeah. The question was about heavy elements, how they're produced in stars. Or heavier than hydrogen, helium. So basically, I did say that just right at the beginning, basically there were only three kinds of elements that chemical elements that were produced, or these were the light elements: hydrogen, helium. And I assume that your question is going in this direction. There's something that is called nuclear fusion. Small particles under such immense power bashing into each other, and the energy is just so intense that the atomic forces in these crashing particles will be so strong that they'll reform, and that's fusion. This is what actually happens in the core of every star in a sun, but up to a certain point only. So, say up to about iron. That's along halfway along, or not quite, and everything else heavier elements will have had to have come out of different stars, out of neutron stars. So that means our sun is not one of these neutron stars. So even all the heavy particles that we have here on Earth, even what you're made of, what your body is made of, and I think that's what you're asking about, come from the heart of a star. It's true. But that star, unfortunately, had to die for you because it needed the explosion to reach us here, so that all these nice iron and heavier particles, elements, come here. Another question from the floor. I have a question about the Big Bang. You said the 13.7 billion years ago, the Big Bang, but what was it with 100,000 years delay? So if everything we have in the visible universe today, all the energy and matter, if that was closer together at some point in the past, that means that all this energy must have been compressed, including dark matter and dark energy, must have been compressed in a much smaller space, must have been just principally closer together. And that doesn't mean anything else but what is heat? Heat is just particles closer together, more movement. That just means it was hotter. So if we go back all this way, we have, first of all, maybe we have a universe very, very cold, maybe close to the absolute zero, which is 270-something Kelvin minus 2 Kelvin. And if once after the Big Bang, it must have been so hot that electrons and protons weren't actually distinct particles, parts of particles. This was just a plasma. This was like a soup of intransparent mess of energy. That means there's no actual means of transportation, or no way for the light to pass through as a distinct thing. It's just like a milky, opaque soup, and that's just a limit of how I can't look back any further, in the same way I can't look through the ceiling of this tent, for instance. Another speaker from the floor. I'd like to say thanks for the talk, first of all. If I understood if I understood it correctly, all the matter was concentrated in in a very small space, and if I were to take just one part of this, I would have a black hole. Why then did the universe expand? Response? Well, no, that's actually not correct. That's not how you get a black hole. What happens in a black hole, or how to get a black hole, is that we have a concentration of matter in a space small enough. It's simply a matter of the black hole. It has to be concentrated in such a small space that the gravitational effects are limited to the black hole. But if surrounding the black hole is just more of the same mess, then this won't be a distinct energy concentration. Then the energy will obviously dissipate. But of course, there were numerous, uncountable black holes that did appear even right after the Big Bang. And this was quite recent research, actually. A few weeks ago, you might have seen it in the news. And there's been some more debate about dark matter. And their idea was that these black holes can actually be understood better through what they called primordial dark matter. So you can imagine what that means. This is a black hole that has the mass of several thousand suns. I think I didn't get that, sorry. But there is a distribution of these black holes. They appeared in the same way at the same time after the Big Bang. Usually you can't see them, but they're black holes. And so we're just expecting them to be sort of distributed equally throughout space. Me personally, I'm not quite convinced regarding this new research. This is actually very current, but I'm not convinced necessarily about the primordial black holes yet. Any other questions? And another question from the floor. I recently saw a panel talk.
Recently, I've seen a panel discussion if the universe isn't just a computer simulation. And one of the arguments was that the universe is not continuous. This would make sense to save processing power. Are there examples from your backgrounds that would speak against this theory? I'm taking part in this discussion if the universe is computable or not. And there is a whole string of theory that is dealing with this and is dealing and to explain it mathematically. And of course, you can explain it this way. Anything in this universe can be explained mathematically. Even random stuff is explainable through Schrödinger's equation. And now we have to see the difference between mathematical possible and computable, because not every equation is computable is to solve in this means. And I want to add, I can imagine a universe, I can imagine to simulate a universe that is not going in steps, and I can simulate a universe in a way that it's not going step by step. For example, fractal algorithms work perfectly to simulate this without these steps. And for example, if I have the time, I can even mathematically calculate even more exact if somebody's taking an exact look at a certain aspect. And this is not a very strong argument. I can focus on certain aspects. And just because we are seeing certain steps of the simulation, we cannot derive from this that this is an argument for the simulation itself. But you cannot contradict, you cannot falsify the idea that the whole universe is just a simulation from whomever. For example, you cannot say that it's just that DNA is not derived from this history, but it was just a circuit made up by a computer that is now simulating the whole universe. I don't think it's very probable, but the idea exists and I cannot deny it. Are there any further questions? I just showed up recently and I wanted to ask about the change of space itself or the quantification of space. What derives from this? So the quantum properties of space is the holy grail of physics. The theory of unification of quantum mechanics and Einstein's relativity theory is the holy grail of physics. But nobody can explain this to the extent. This so-called theory of everything the so-called M theory, an addition of the string theory, and I personally don't like it because it's so random, it's so abnormally random, and it hasn't been proven until today. Everybody who has too much time in theoretical physics but want to win a Nobel Prize in physics are dealing with this question. But it's not working until today. We haven't figured out. This is one of the biggest dilemmas of our time. But it's not so far in the future, one could say. If you think of artificial intelligence and fusion reactors, the quantizing or of space hasn't been explained today. Not in one theory. There are certain aspects, but they all hit the fan at a certain point of time. We have still 4 minutes to go. 1-2 questions we will still be able to answer. What is the quantelung of space? Quantification of quants of space. Do we get the properties of space explained? And can we present this in space? Are there steps in space itself? Does a space exist that has only 1 to 3 or 3 units, or the size of 1 or 2 or 3 units, or half, or 2/3? Is there something like the smallest unit of space, and the whole space is built by these small units? There's the idea that this exists. There's something of the smallest length, the so-called Planck length, and everything that is the Planck length would become a dark hole instantly. This is why the Planck length is the smallest length that is imaginable by physics. But the question if space could be 1.5 Planck lengths, there is no answer to this question. There's no working theory dealing with this that can explain it. And everybody's working on this because if you can figure out, everybody's working on this because if you can figure out, you're the next Einstein. Another question. Is there one last question? Can you tell us from which point of Newton mechanics gets fuzzy in terms of speed, length, time? I'm very this is a German thing. He's giving him the respect form. From which point on does Newton quantum mechanics doesn't work? So this Newton theory is really, really good. From certain speeds, it doesn't apply anymore. Let me give you an example. If we look at planets, how they circle around the sun, that Newton mechanics gives you perfect explanations how these planets circle, and is explained really well by Newton's mechanics, except for Mercury. He is so near to the sun, he's so enormously fast that Newton mechanics cannot explain Mercury. And Newton was annoyed by it himself. And I couldn't give you a better idea of how to explain this limit. You could give another example, just hypothetically. For example, if you look at the Bohr's idea of the atom. So this Newton's theory explains until to silver. Gold is not white anymore because the electrons because in Bohr's model the electrons are so fast that relativist effects that they absorb certain wavelengths that they weren't supposed to absorb. This is this is why gold is not white, because of certain problems in Newton's theory. I think we are done. I want to say thank you that you've listened to this talk, even though you're on Fusion, but also because of your Fusion. I didn't think 10 people would show up. I thank everybody in the audience, and I thank you for your patience and for your interest. Thank you very much.
And that was Anwen and Fabian from the Translators. Thanks for listening in, and give us your feedback if you like anytime.